So in this lecture, I'm going to walk you through some notes that I have prepared on simulating data for computing type 1 error and statistical power when you have repeated measures data. Okay? So there are several reasons why you might want to do type 1 error calculations and power calculations when you have a linear mixed modeling setting. Well, one reason would be to decide on the number of subjects that you might need. So suppose you have some prior data, pilot data, or a previous experiment or somebody else's experiment data. You can use those data as a starting point for doing some simulations to understand how many subjects you might need to have adequate power. Type 1 error calculations are also very useful to do with simulation because they illustrate the very important insight that we gained earlier in this course, that um, if you oversimplify your linear mixed model, your type 1 error will inflate. That's the Barr et al. 2013 paper, right? So if you make your model overly simple, your type 1 error will go up. And so you don't want to make your model overly simple for that reason. All right, so those are two good reasons why you might want to simulate data. Another good reason is to pre-register your study before you actually carry out the analysis. So you should look at this paper, which appeared somewhere, I don't know where, but it's a good paper. So you should look at it, and it will explain why you need to do pre-registration and how you should do it. I'll talk about this at some point in the final lectures. All right, so getting back to my lecture notes. So the goal is simply to learn how to do type 1 error calculations and power calculations using simulation, right? So what I'm going to work with in the beginning is a very simple data set. So this is from the LinkPsych library. It's an English reading study, self-paced reading. And in this study, we have only two conditions, grammatical and ungrammatical. They're already coded +1, -1. And again, it's a standard Latin square repeated measures design. And this is reading times on the log scale at a particular region in the sentence. Okay, so that's the setup. Very straightforward. The data come from this paper from 2011. It's one of my lab's papers. All right, so in this setup, what we have is grammatical sentences are coded as +1 and ungrammatical sentences are coded as -1. So you can see the difference in reading time on the log scale between the two conditions. The grammatical sentences are somewhat harder to read than the ungrammatical sentences. Okay. Interesting result, right? Because normally you would expect grammatical sentences to be easier to read. So that's a fascinating problem that has been studied, not a problem, but a fascinating phenomenon that's been studied in psycholinguistics. Why certain grammatical sentences are hard to understand, but their ungrammatical counterparts are easy to understand, or they seem easy to understand. It's an illusion of grammaticality. Okay? So it's a very interesting topic, but we won't get into the science of this yet or at all. But let's talk about the actual nitty-gritty details. I have this data, and I'm going to use the data as starting point for simulating some future data, right? And so first of all, we'll check that the data come from a Latin square design. This is all stuff we've discussed in the past, so I won't go over this again. Subject and item crossed. If I do an X tabs on subjects and items, I should see at most the number 1 for every subject. So each subject should be seeing exactly one item, right? So you can check this yourself. Now, we are going to recode the predictor. So the grammatical condition is coded as +half and the ungrammatical is -half, and that's only because I want the slope to represent the actual effect size that I'm investigating. Okay, so the model that we will fit is like intercept plus +half -half coded predictor, right? Grammaticality, varying intercepts and slopes without correlation for subject, varying intercepts and slopes without correlation for item, all standard garden variety stuff. When you fit the model, you will find that the variance components are problematic. So there's in the items intercept, we have a 0 variance component. That means the model failed to estimate the this variance component, and that's mainly because there are very few items in this data set, 60. Okay, because of the nature of the design, it was hard to come up with a lot of items. We have 48 subjects, so we generally have a better control over the subject's estimate, so we can get better estimates of the subject variance components, intercept and slope. That's normally the case because we usually have much more subjects than items, right? Now in the items, you'd see that the intercept standard deviation estimate is 0, but the slope standard deviation estimate looks like it's not 0, but this is 7.359 times 10 to the power of minus 6. That is basically 0, so it's very close to 0. So the item variance components are apparently not working out very well, can't be estimated well, and that's why you're getting this singularity warning. Right? Okay, so nevertheless, I ignore all those problems for now because I wanted to show you a situation where we have 5 variance components, residual, plus subject and item variance components, right? So we have a significant effect here. So very large t-values. So we have very strong evidence against the null. But what we want to do is we want to carry out some power analyses to find out what sample size we would need to achieve, let's say, 80% power. And if we ran the same experiment again, right? So this is all about the future. Power is all about future experiments. It's not about the current experiment, right? So I can't get any information about the power of this particular experiment after I've done the study. After the study is done, we only have the p-value. The power, after you've done the study, the statistical power is just a transformation of the p-value, okay? So it's not, there's no new information about power or no information about power in an already done study. We're talking about a future study here, okay? So we want to know, how we can generate some simulated data using the estimates of the parameters from the fitted model. So what are the estimates? Intercept, slope, fixed effects, okay? And then these 1, 2, 3, 4, 5 variance components. So there's 7 parameters that I'm going to use to generate some new data and check in what proportion of cases I actually reject the null hypothesis, okay? Notice that if I assume that this is the slope, I'm assuming that the null hypothesis is false, because the null hypothesis is usually that the effect of interest is 0, okay? And it's clearly not 0 here. So I'm going to be doing a power analysis. So we do this, we will simulate data using the design R library. The way you do this is first you install the design R library. You can do that in the standard way, install.packages, etc., etc. This web page just provides some documentation that you can look at later. And it was designed by one of our former PhD students who's a postdoc now in Potsdam in psychology. Anyway, so we have the design R library, which will help us simulate data. And the advantage of the design R library is that you can abstract away from the low-level details, of generating data, and you can focus on the main issue at hand, which is to get the specify the model and generate some data. Sorry, I have very bad allergies right now. Okay, so right. So how does this design R package work? First, you load the library. Then you have to define the number of subjects you have per condition. Not the number of subjects overall, but per condition. So if I have, let's say if I specify 40 subjects per condition, and if I have 2 conditions, then how many subjects do I have in total? 80, right? So don't be confused about this. If you write the wrong number here, if you think that this is the total number of subjects, then things will get messed up for you, okay? This is the number of subjects per condition, and I even said that here. So don't mistake this. So in the design R package, there's a function called fix.factor, which which allows you to define the fixed factors um, in your experiment. So what we have is we are creating a new factor level. I'm just calling it fgram factor grammaticality. Just I could have called it anything. Okay, doesn't matter. You choose some name that's reasonable, and the two levels I'm calling grammatical and ungrammatical. So that's how you specify the fixed factors. Then you add a plus sign, and then you specify all the random factors in the design. Okay, so here's how we do this. First, we define the random factors for subjects. Okay, and what we say is that we have the number of subjects that we have per condition is called the instances in this design R package. It's just an arbitrary terminology. Okay, so that determines the number of random intercepts you will have for 80 subjects now, because this number of subjects per condition is 40. Okay, and there are two conditions. It knows that there are two conditions because you specified that here. Okay, if there were 4 conditions, then you would write the two factor levels, right? There will be 2 factor levels, and then there would be two factors with 2 levels each, in a 2 by 2 design. I will give an example of that in class. Okay, so in any case, now we are talking about the random factors for subjects. So we specify that, that's it, and then plus the random factors for items, same setting. We have the number of items, remember, was 16, so 8 per condition. Okay, 8 times 2 is 16 items. So you have to remember that this is a slight, possibly confusing detail here. Okay, then you say, so now you specified the number of subjects and the number of items. That's what these 2 lines do. And what the last line does is that it says that the subjects and the items are going to get repeated measurements from the factor of interest. So what was the factor or the group? This is the grouping factor, right? This is the factor f gram. So there will be repeated measurements from each subject in each level of the f gram factor, repeated measurements for each item in each level of the f gram factor. That's what this line is saying. So all of this is one statement plus the second statement plus the third statement, and then finally plus the last statement. All of this goes into the design object. It's called the design object, where I'm saving the basic specification of the experiment. And then I take the design object that I just created, I put that in through this function called design.codes. And what that does is it creates a data frame for me, which has the subject column, the items column, and the condition column, but it doesn't have any data. Okay? So it just lays out the design row by row in the data frame. So if I look at the simdat object that I just created with the design.codes, what I get is a data frame that contains subjects, items, and the factor levels of the f gram factor. You can check now, just a sanity check. The number of subjects is 80. The number of items is 16. Okay, and now what I'm going to do is I'm going to create a gram variable in the simdat object that recodes the f gram factor levels to plus half, minus half, just like before, right? So now I have contrast coding here, the sum coding ready. So I'm getting to the point that I'm going to use this data frame to create a new column that contains simulated data again and again. Each time I'm going to put in new simulated data here. Okay. All right, so here we go. We're going to generate data repeatedly, assuming a particular effect size. And so the way we will do that is that we use this sim capital LMM function from the design R library, and we use that function to generate simulated data that we're going to put into this vector in the data frame simdat that's called ysim, simulated y dependent variable, right? So in the sim LMM function, what we have to do is first to define the linear mixed model formula. So you just define the right hand side. So you don't write y tilde gram, you just write tilde gram and then the intercepts and slopes. I put a single variable here, but I'll explain why I did that, right? And similarly here, I put a single vertical bar here. Even though when we fit the data earlier, I used a double vertical bar, assuming, that is, I was assuming no intercept slope correlations, right, for subjects or for items. But in this formula, I'm assuming that there is an intercept slope correlation, okay? But I'll just explain why I did that, okay? Then I put in the SimDat object that I had just created, the data frame that contains everything except the simulated data. So I'm going to plug that in here, okay? So now this SimLMM function now knows what the data frame should look like, what the structure of the experiment is, what the design of the experiment is. We created that earlier, okay? Now the remaining steps are to just write the fixed effect vector. This is a vector that writes the intercept estimate and the slope estimate. So I just put in 0.1 as my slope estimate, even though in the actual data set, what was it? It was 0.35, right? 0.35 is a gigantic effect on the log scale. This would give me a power of 1, right? So just for illustration, I've made the effect size smaller here. So my effect size is a bit smaller here, okay? Just for illustration. Okay, so that's my fixed effect. That's one. Then the next thing I'll define is the variance components as standard deviation. So that's why it's called VC underscore ST. And the variance components will be defined as a list object, which will have 3 elements. Okay, the first element will be the vector of subject random effects, standard deviations. The second vector will be the item random effects, standard deviations, and the last one will be the residual standard deviation. Okay, so these are 1, 2, and 3 elements, list elements in this object here. Okay, so let's just focus our minds on the subject standard deviations. I extracted these. This is the intercept standard deviation, random effect subjects intercept standard deviation, random effect subjects slope standard deviation. So 2.422, 2.7, 2.277. If you go back here, you'll see that I got it from here, right? I hope this scientific notation is clear. What this means is 2.422 times 10 to the power of minus 1. That means the standard deviation is 0.2422. And here also I have 2.277 in times 10 to the power of minus 1, which makes the standard deviation estimate to be 0.2277. Right, so I'm just writing it in scientific notation here because I just copied it over. And R will recognize this, of course, and the SimLMM function will know what this means, of course. For the item random effect standard deviations, I had a 0 here and I had something close to 0 here. So I changed the 0 to a slightly non-zero value, right? Because I know that the items are going to vary. They will be between item variability. I just couldn't estimate it from that data. So I just changed it to some small value to reflect the fact that there will be some between item variability. But I didn't mess with the slope parameter because I could have had a small value there too, but I just copied it over from the fitted model. And this is just the residual standard deviation taken from the model, from the fitted model, right? 4.561, 10 to the power of minus 1. That's my residual standard deviation. So this term here, this part here defines the variance components. This part here defines the fixed effects. So remember I said there were 1, 2, 3, 4, 5, 6, 7 parameters. So there's 1, 2, 3, 4, 5, 6. Oh, sorry. 1, 2, 3. Oh, wait. Where am I? Sorry. 1, 2, 3, 4, 5, 6, 7. Wow. I can add at least. So that's my 7 parameters in the model. And so here comes the point. Here now I explain why I put a single vertical bar here and here. What I'm doing is there's another variable that you can specify when simulating data. It's the correlation parameters, right? So if I wanted to assume a non-zero correlation between the intercept and slopes for subjects and the intercepts and slopes for items, I would put in a vector here with some values like, let's say, 0.6 and 0.6 or something like that. I'm just making the numbers up, but just some non-zero values, right? But I'm assuming zero correlation, and that is identical to defining a model. Assuming a zero correlation here, I've defined zero correlation parameters for both subjects and items. That amounts to specifying a model that has 1 plus gram double vertical bar subject. That's exactly the same thing because I'm assuming no correlation at all. Same thing for the items. So if I specify 0 here, that implies that there is no correlation between subject variance component, intercepts and slopes, and item intercepts and slopes. Okay, so that's the entire specification of the basis for my simulating the data. Then I say empirical equal to false because what I really want is to have randomly generated data. If I had said empirical to true, I would get the same numbers back that I put in, which is not interesting or useful. It's just there for some, I don't know, some obscure reason. I'm not really sure why they put this option in. Okay, it's not ever going to be used by us. It will always be false. Verbose is false because we don't want to receive a lot of information in the output, right? And the family is Gaussian. I mean, that's only because we want to explicitly state that we have a normal likelihood assumed here in this model. Okay? So we are assuming a normal likelihood. That means the residuals are normally distributed. Okay, that's what it says here. All right, so then now we're going to simulate. Now that I've defined, look, what I've done is this long part here. This sim_LMM function creates a vector of data points that are added to the data frame that we had created earlier. So a new column will be created here called ysim that contains simulated data. So this is just one simulation. If I ran this multiple times, each time I get slightly different numbers each time. So we're going to put it in a for loop. We're going to do 100 simulations, and I'll just explain what failed is, but the t-values will be stored. Each time I look at the slope t-value, I will save the slope t-value. I think we did that last semester as well, right? And so the for loop starts here with 100 repetitions. Each time, what I'm going to do is I'm going to run that sim_LMM function I just showed you, this one. This will be run 100 times, and it will generate simulated data 100 times, okay? So I'm going to keep overwriting this column 100 times as I run through the for loop. And every time that I generate a vector of simulated data, what I'm going to do is, once I've simulated the data, that means I've created the data frame simdat, and it now has a new column, ysim, which is the simulated data. What I will do is I will run a linear mixed model, which has exactly the same form as the linear mixed model that I had used for the actual data, right? So double vertical bars this time. And one thing I've done is I've tried to get our Elmer to not display any convergence warnings. Okay, so I run this code. So this code, this is the Elmer function, right? So this produces a model fit for each simulated data set with the parameter estimates that I had. Okay, it generates data, right? And so now I'll explain what this failed is, right? So every time the linear mixed model fails to converge, I want to store that information. So I created a vector called failed, which allows me to figure out whether I got a convergence warning or not. I'm just bookkeeping. Like you could ignore this part of the code, you know. So you could just not pay attention to it and not use it, right? If you don't want to track the failed convergences. But I just wanted to track it to see how many times in 100 repetitions the model fails to converge. So what I'm doing here, this code, what it does is it says that if there is any output that says fail to converge, or it says boundary or something like that, these are the two messages that come out, you know. Then in the failed vector, in the ith iteration, I will store a 1, otherwise I will leave it empty. Remember what the default value was here? The default value is 0, right? So the failed vector will contain ones. It'll be a vector of 100 elements, and it will contain a 1 just in case the simulated data led to a model fit that did not converge, okay? To a model that did not converge. So that's what this code does. If there's a convergence failure, I save that information in the failed vector. If there is no convergence failure, that's the else condition, then I will save the model's t-value for the slope. Here's the slope, here's the t-value for the slope. I save it in the ith row of the 100 cell t-vals vector, right? So this is my entire for loop, right? So this for loop ends here, it ends here, it begins here, okay? So you can run it yourself and see, and we'll do it in class also, okay? So now, once I run this for loop, what will happen is I'll get a vector of t-values. So I can look at the vector of t-values as a histogram, and what I notice is that anything above 2 is going to be a significant effect, anything below -2 will be a significant effect. So what I find is, what I ask now is, what is the proportion of times that the t-vals vector has an absolute t-value that is larger than 2? Because those are the significant results, right? So I calculate the mean proportion, and that's 59. So that's my power. For 80 subjects and 16 items, that would be my power. If I were to increase the number of subjects now to, I don't know, 120 or something, so 240, no, 120, that means I would have to halve that for each condition then in the specification, then my power would definitely go up, okay? I could also increase the items arbitrarily, and that will also lead to power increase. But remember that in a real life experiment, you can only show so many items to a subject before the subject gets exhausted. So you can't just arbitrarily keep increasing the number of items in an experiment. The subject will suffer so much that they won't give you any useful data. So there's actually a practical limit, you know, over which you cannot go if you want to increase power by increasing the number of items. Okay, so subjects you can increase as long as you have money and time, you can do that. So that's where I usually focus my attention, you know, not the items. Another reason not to worry about increasing the number of items is that what you will usually find in a planned experiment is that this is almost always true. Okay, in a well-planned experiment, the largest source of variance is always the residual. Always. This is the biggest source of variance. The random error is the largest source of variance, and the subjects are the next two largest source of variance. And the items usually have very low variance. You know, the standard deviations are very low. And the reason for that is that it's a planned experiment. The items are designed to be similar to each other. So they don't have much between item variability, right? So because they have small variability, the standard deviations are gonna be small. They don't contribute that much to power, okay? So therefore, it is the real payoff in increasing power comes when you start increasing the number of subjects. Like, at least that's how I see the situation, okay? And that's what that's what I do in practice, okay? When I'm doing power calculations, which is never, of course, right? So I use Bayesian methods, but that's a separate topic. So anyway, so where are we? We ran the for loop, and we got our t-values. We know what the power is, and we also know the proportion of failed convergences. So I've got 13 failed convergences. That's useful to know, okay? If I were to increase the number of subjects and also increase the number of items, let's say to double that number, then I would get fewer failed convergences. Try that out yourself. You will see that there'll be fewer failed convergences. Another way to decrease the number of failed convergences, right, would be if the variance components for items were increased. Oh, sorry, where is this? Here, right? I'd set these variance components to be very low. Notice that here I made them a bit larger, right? If I made these just as low as these values here, then I would have many more failed convergences. The proportion of failed convergences would go up dramatically. Yeah, it wouldn't just be 13%. And that would be because I have such tiny variance components for items that the model just cannot estimate it. And it just keeps returning a failed convergence there. Because the value is too small, it's too close to zero to estimate, right? So we'll do some exercises with this in class later on so you get a better idea. Now remember, I was calculating power. So if I have 59% power with 80 subjects, I'm not going to be too happy about that, right? So I would want to increase the number of subjects, maybe double the number of subjects and see what power I get, and it should go up. Okay, so that would be the usage of this thing. Now we can write a general function that simplifies our life because this is too much hassle, right? If you look at all this code, am I going to have to write this code over and over again just to do power calculations? No. Just going to write it once, wrap it in a function. I'm going to create a function called compute power and I'm done, right? So I just write compute power and I run the function. That's it. Okay, so that's what I did here. So I'm going to define a function called compute type 1 power. The reason I say type 1 as well is because here, when I specified the fixed effects, right, in this for loop, if I specify the slope to be 0.1, I'm assuming that the null hypothesis is false. And that's going to give me the statistical power, the proportion of times that I would actually correctly reject the null. Okay, but if I set the slope to be 0, then the null is true. And now the t values that I will get, these t values, right, they will be telling me the proportion of times that you are incorrectly rejecting the null, because the null is actually true if you set the slope to 0. So those t values, this very same function that we have here, or rather the very same function that, the very same function that we have here is going to give us either type 1 error if we set the slope to 0, or statistical power if we set the slope to non-zero value, or some non-zero value, right? Okay, so that's why I call it type 1 power, right? It's the same function for computing both type 1 error and power, right? So now what we're going to do is, in this function, I'm going to set some parameters. The number of subjects per condition I have to specify, the number of items per condition have to be specified, the effect size has to be specified. I've written this function specifically for this data set, okay? But I could write a more general function if I wanted to. But just for this data set, I've written one function. So the grammaticality effect is set at null, but you have to specify it. So I specifically set it at null so that you're forced to decide on the effect size yourself, okay? And we do the number of simulations at 100, but you could increase it to 1000. In fact, in practice, I would run 10,000 simulations because I just have to wait a little longer. That's all, you know. And then here is a command called maximal equal to true, where I specify whether I want to assume a maximal model, like it was discussed in the earlier lectures. That means whether I want full variance covariance matrices for the items and subjects. Okay. If I set it to false, then I won't fit a maximal model. So you'll see the code in a moment. So then I repeat the code that I showed you earlier. This is my design. This is my design code that sets up the data frame without any reading times. And so I set up the run the design object through the design codes function, create my simdat object, and then I recode the predictor as plus half minus half, just like before. Then I set up my t-vals vector where I will store my t-values for the slope, and then I just run the very same for loop with some values for the intercepts and slopes. And notice here that I'm using now the grammaticality effect which I specify in the function here. If it's 0, if I specify the grammaticality effect to be 0, then I'm studying type 1 error. If I specify it to be a non-zero value, then I'm studying power. Okay, same code. Right, so then, so here's the maximal equal to true thing. If I specify this to be maximal equal to true, then I would try to fit a maximal model where I have both intercepts and slopes, but no correlation, because I know that I'll never be able to estimate the correlations anyway, right? So that's why I'm calling this a maximal model. And in fact, the word maximal is kind of ambiguous, underspecified. In the literature, in Barr et al., what they meant by maximal was either a model with both varying intercepts and slopes and correlations for subjects and items, or varying intercepts and slopes but without correlation. And they're kind of vague on that point. Okay, so we can call this a maximal model. All right, so this is all set up here. If I don't want a maximal model, if I set maximal equal to false, then I just fit varying intercepts. And you know what's going to happen if I do that? My type 1 error is going to go up dramatically. Okay, that was the Barr et al. Paper. So if I set the grammaticality effect to be 0 and say maximal equal to false, what's going to happen is that this simulation is going to run a varying intercepts model only, and I can guarantee you that your type 1 error will not be 0.05. It will be something like 0.15 or something even higher. Okay. Anyway, so the rest is all bookkeeping. It's all straightforward. And here I'm just printing some results. Like if the grammaticality effect is 0, I say that the estimated type 1 error is, and then I compute the proportion of times that the absolute t value is larger than 2. And if the grammaticality effect is not 0, so that's the else condition, then I would return estimated power is, and then the same quantity again. Okay, so that's it. Let's test the function now. Okay, so here's the function: compute type 1 power, number of subjects 40, number of items per condition, number of subjects per condition 40, number of items per condition 8, grammaticality effect 0. So now I'm studying type 1 error, right? Maximal equal to true. If I run that function, I've hidden the output, I get a type 1 error which is close to 0.05, right? Now I had only 100 simulations. If I ran 10,000 simulations, I would get a value near 0.05. Okay, very close to 0.05, but this is also pretty close to 0.05. If I were to run the same thing again, so then effect size is 0, but maximal is false. Now look at the type 1 error. Right, it's inflated now because I fit an oversimplified model with only varying intercepts. Now the practical implication of this is that, sometimes what people do when they're publishing papers is that they're desperate to get a significant effect, because they know if they can't get their p-value under 0.05, they won't be able to publish that paper. So in their desperation, what they will do is that they will, instead of fitting the appropriate model with varying intercepts and slopes for subjects and items, they will fit an oversimplified model with varying intercepts only. Why? Because that will give them a higher type 1 error, and so they will have a higher probability of getting a significant effect, even if the effect was not there. So this is something that people do to, I guess I want to say, get ahead in life. If you want to just publish papers without regard to whether you actually truly found something or not. So, but this was the big insight of the Barr et al. Paper. Okay, so the Barr et al. Paper, where is it? Sorry. So the Barr et al. Paper. Here, this one, in the Journal of Memory and Language. This paper appeared in 2013, and it had a dramatic impact on the field. People finally realized, I also realized, I didn't really appreciate this point, people realize that it's important to take into account all the variance components that are justified by the design. Okay. The only problem that you face when you do that, when you try to put in all the variance components, is the convergence warnings. And so there was a big controversy about whether the convergence warnings matter or not. There are different opinions on this. We can discuss those in class, okay? But that's the main point of the bar et al. Paper, and we should really not do the wrong thing and fit overly simplified models. Why? Because that inflates our type 1 error, and we don't want an inflated type 1 error in our experiments, in our papers, right? Oh, now you can like fool around with this function to see what's going to happen. If I set my effect size not to 0 but 0.08, maximum true, I get 63% power. If I increase the effect size to, or if I increase the number of subjects from 40 to 400 per condition, from 40 to 400, that means if I have 800 subjects, I end up with 100% power, right? As you would expect. If I increase the effect size to double the size, more than double the size that I had assumed earlier, I again get an effect size of 1. So it's the same situation as in power.t.test. Effect power depends on effect size, standard deviation, in this case the variance components, and the magnitudes of the variance components, and the number of subjects. 3 things determine power. Okay, right. So we'll do a class exercise which I wanted to release to you in advance, and we'll discuss that in class. So that's my introduction to simulation. In my next lecture on simulation, I will demonstrate how you can do power and type 1 error calculations in logistic mixed effects models, so in the generalized linear modeling case, right? Unfortunately, this design R package does not, there is no functionality for logistic mixed effects models, so I will write the code myself and demonstrate to you how you can do the simulations very easily, okay? So that will be the next lecture.